if you look at the examples that we did, they were of these three forms. So I just wanted to review sort of what we did here. So for the first example, we have this guy. The triangle looked like this. A, you're taking x from A, so A has to be the hypotenuse. So I put x here. Then the square root ends up here. And your substitution ended up being x equals A sine theta, which we can see because sine theta is the opposite over the hypotenuse. Okay? This guy was our second example. In that second example, when we drew the triangle, we could see that this x is what we're taking stuff away from. That's going to be our hypotenuse. And what did I want? Because I wanted secant, so I put this A here, and then this guy ends up being my square root. And then because cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent, and then it becomes x equals A secant theta. This guy then was our last example. The difference here is, of course, that it's a plus, which means I know immediately that that whole radical then has to be here on my hypotenuse. A squared plus x squared. And as far as the legs, because I want a tangent, I put x here and A there. So tangent of theta is x over A, or x equals A tangent theta. You may also see integrals that have not just the square root, but perhaps they have the square root squared, right? So just the thing here. So for example, if I was integrating something like a squared minus x squared, I can't do that I can't do that, we can't pull off the a squared, right? I don't have a du for natural log, so this would be one which would be good to do with this, or possible to do with this. So let me put in my dx so I know that it is dx. You might also see the square root in the top rather than the bottom. I think all three of ours, it was in the bottom. It may be, or also you might see the square root to the cubed, so it would be that expression to the 3/2. So sometimes you may see such things. So as I was saying, I might have something like this. X squared minus a squared, just like that, no du, extra du, no x in front here. I might have something like 1 over a squared plus x squared to the 3/2. So kind of keep this in mind, that this is a possible technique to use. Now, I also want to go and give you some hints about sometimes we can actually get away with not using this technique, right? So here's some examples. Let's just take our first example that we did, which was this. Right, well, this one we had no choice. We had to use trig sub. However, and I think I mentioned this on the video, if it just looked like this, I could use u sub, right? Because if I did u being 9 minus x squared, then du is minus 2x dx. And I can substitute in here, my integral is going to become minus 1/2 du over the square root of u. So anyway, it just becomes u to the 1/2, right? So this is a simple u substitution. That extra x throws it into this, trig substitution. Now it's a bit of a hoopla, right? The interesting thing is you can use u sub sort of this way. It's very similar. This is very similar to what we did with the trig integrals actually in section 7.2. If you have an odd power of x, like x to the 1, right? It's pretty obvious, but look, I can with x cubed, I can also do a u substitution here. I could also do a trig substitution there, okay? So if you didn't realize you could do u sub, I'll show you what happens with it and we'll do it. But if you did trig sub and you did it right, you would get the right answer, okay? And it may turn out to be not as unpleasant an integral as that one, because you just never know. But because you have an odd power, what you can do is you can kind of, using this same substitution, right? We can kind of pull off that x dx. Okay? So here, our x dx then turned into be 1/2 du, minus 1/2 du. So I can do the same thing here. I've got this extra x squared. So what do I do with that extra x squared? I can solve this part of the u substitution, right? And I can solve for x squared in terms of u. Okay? So let's do that. I'm trying to think about how I can do this. Let me get rid of this. And then I can write it here. So then I have, right, x squared is 9 minus u, right? If I just solve for x squared. So I can substitute, and this one I can also just do x dx is minus 1/2 du. We did that in our head, but I'll write it there just because now I want to make sure that I get all my minuses straight again. So substituting all this in here gives me 9 minus u times negative 1/2 du, and this is all going to be over the square root of u. Okay? So let's see if I have enough space to write this so we can see what this becomes. I have pulled out the negative 1/2, and then I have 9 minus u over the square root, so I can break that into 2, right? 9 over square root of u minus u over square root of u. And then I can just continue from there, right? Because this is 9 u to the minus 1/2 minus u to the minus 1/2, u to the 1/2. Right? So in this form now, I can do that in a pretty straightforward way. The reason that I couldn't really do that here, of course, is because I didn't have that extra x. So I didn't have anything to put into my du. And if I tried to solve this, I'd end up with a square root, and I would just be a square root. It wouldn't be any better. Trust me, it's not a good situation. Doesn't work out, unfortunately, right? So sometimes those kinds of things work out, other times no. And the reason you can do it is you can, as long as you have an odd power, and the odd power is in the top there, so that it's multiplying by the dx, you can use this little u substitution trick and then solving for these guys in order to not do the trig substitution. It doesn't work if you have even powers of x, no powers of x, right? 0 is like an even power. And it also doesn't work if your x is in the denominator. So if I had like this, x cubed square root of 9 minus x squared dx, yeah, it's an odd power, but it's in the denominator. I can't really put it with a dx and make this substitution. It doesn't work. So for this one, I would have to use trig sub as well.